In this chapter, we are going to move away from the irreversible reactions we are used to seeing and studying reversible reactions. An irreversible reaction is those that proceed until one of the reactant is used up. The reaction does not proceed in the reverse. It goes to an end. There are two situations that give rise to an irreversible reaction. A highly exothermic reactions are generally irreversible because the activation energy for the reverse reaction is so high. For instance, a hydrocarbon combustion reaction. Another situation would be when reactions where products are removed. For instance, if a gas is formed and released, or if a precipitate forms when ions unite into solid crystals. This would be an irreversible reaction. Irreversible reactions are always represented by a single-headed arrow, and these are the types of reactions that you've probably studied in Science 1206 and Chemistry 2202. In this chapter, we're going to look at reversible reactions. A reversible reaction is when the product can reform reactants. One of the best examples of a reversible reaction would be any sort of phase change. For instance, if I take liquid water and put it in an ice cube tray and place that tray in the freezer, it will freeze to solid ice. That's reversible. I can take the ice out of the freezer, lay it on the counter, and before long it will be back to being liquid water. Reversible reactions give rise to an equilibrium, where both reactants and products are present. Equilibrium reactions are very important in chemical industries. For example, the Haber process produces ammonia, which is used to make fertilizers. Industrial chemists are not only concerned with controlling the reaction rate or how fast this happens, but also with manipulating the conditions of the reaction so as much product is formed. We are going to be looking at dynamic and chemical equilibriums. A dynamic equilibrium is a process in which two opposing forces are happening at the same time. For example, the rate of dissolving and the rate of crystallization. Chemical equilibrium is attained when the rate of the forward reaction equals the rate of the reverse reaction, meaning how fast products are formed is how fast reactants are formed. We do not need to have the same concentrations of reactants and products, we just simply need to be making them at the same rate or at the same speed. It's dynamic in the sense that the reaction never stops shifting from forward to reverse and back again, like a seesaw. There are three conditions that are necessary in order for an equilibrium to occur. First, it can only occur in a closed system. A closed system is one that is closed to the flow of matter, meaning matter cannot enter or leave, but open to the flow of energy, so heat can be added to the system or the system can be cooled down. What this means is that equilibrium can only occur in a system that is stoppered. As well, the macroscopic properties like color, temperature, pressure must remain constant. That means that the observable properties must look like nothing is happening. Lastly, the reaction itself must be reversible. A reversible reaction is one that can go forward from reactants to products and in reverse from products to reactants, depending on the conditions. We use a double-headed arrow in order to represent that in a balanced chemical equation. It could also look like this. There's no net change in concentration of reactants or products occurring. Some of the macroscopic properties that one can observe to see if an equilibrium has been established would be color intensity. So if there's no change in color, then it's at equilibrium. The amount of solid material at the bottom of the reaction vessel, if that remains constant, equilibrium has been established. If the pressure, the temperature, or the volume of the system remains constant, we can also say that equilibrium has been established. We can now look at how a reaction proceeds as it sets up an equilibrium. Remember that for a forward reaction, we mean that reactants are making products, and for a reverse reaction, products are making reactants. At the very start of the reaction, for instance, as soon as you were to start a stopwatch, the forward reaction will be very fast, seeing as you just introduced reactants to each other. They will have their maximum concentration, and according to the collision theory, you'll have a very fast reaction rate. The reverse reaction is not significant or is not happening at all. If you think about the fact that you just started the stopwatch, we haven't had enough time to even make products yet, let alone for the products to remake reactants. However, as time passes, the forward reaction will always be slowing down. The reactants are being used up, so their concentration is decreasing, so the reaction rate will be decreasing. The reverse reaction, however, will always be speeding up as time passes. It will always be speeding up because if you think about it, at the start of the reaction, it wasn't happening at all. As time passes, reactants are making the products, and now as the products are building up, they can reform the reactants, so it will be speeding up from zero. As soon as equilibrium has been reached, by definition, the rate of the forward and the rate of the reverse reactions will always be equal. This gives rise to two rules before an equilibrium is established. Before the equilibrium is established, the forward reaction is always faster than the reverse, but the forward reaction is always slowing down and the reverse reaction is always speeding up until they go at the same speed. We can represent this idea graphically. Let us first look at the first two graphs. Notice that we have a reaction of carbon monoxide reacting with hydrogen. When the carbon monoxide reacts with the hydrogen and they're first introduced to one another, the reactants will start to make products. Since the reactants are starting to make products, their concentrations are decreasing. This is represented in this graph, where you can see that from the start, the hydrogen and the carbon monoxide concentrations are decreasing. Recall that as soon as you start the stopwatch, no products have been made. This can be represented in the graph of methanol by the fact that the graph starts at 0, 0. But as time progresses, we're going to make more and more product. This can be represented by the shape of the graph of methanol. Notice that eventually all species, so the hydrogen, the carbon monoxide, and the methanol, all flatten out to a horizontal line. The horizontal line represents the fact that equilibrium has been established and there's no changes in the concentration going further. We can take these two graphs and we can superimpose them and make one nice graph showing the changes in the concentrations of reactants and products. Again, as time progresses, the reactants are decreasing, the concentration of the products are increasing, until we reach such a time that equilibrium has been established. And at that time, going further, you'll notice that we have horizontal lines. So by looking at a graph, you can tell what time equilibrium was established, and you can also trace across to see what the equilibrium concentrations of all species in solution would be.